Sathyabama Institute of Science and Technology.
Hello everyone, I am Dr. Annie Micheal, Assistant Professor, Department of Computer Science and Engineering from Sathyabama Institute of Science and Technology, and today we are going to see about the topic optimization in deep learning. So before moving on into optimization in deep learning, first let's see what is deep learning. So deep learning is a subfield of machine learning. It focuses on artificial neural network to perform a task without explicitly programming them. For artificial neural network, they are modeled after the structure and function of a human brain, and it consists of layers of interconnected nodes that process and transform your input data. So deep learning algorithms, they are composed of multiple layers of interconnected nodes, and these interconnected nodes are known as neurons. So nowadays, deep learning has significant success in various domains such as computer vision, speech recognition, natural language processing, and etc. Now let's see the difference between machine learning and deep learning. So for machine learning, we have an input data which is a car image, and from this car image we are going to extract features of the car such as shape and texture of the car, and after extracting the features we are going to classify it, and we have two class labels here, car and not a car. So since the image has a car, your output will be a car class. So next is deep learning. So what is the advantage of deep learning is when we are giving an input, it will extract the features automatically and it will classify it in a single neural network which consists of multiple layers, and you will get an output as a car. So now let's see the deep learning benefits. What are the benefits? First benefit is automatic feature learning. So deep learning algorithms, they can automatically extract the features without the need for manual feature engineering. The next benefit is handling large and complex data. So deep learning algorithms, they can handle large and very complex data which would be difficult for a traditional machine learning algorithm to process. The next benefit is pattern discovery, and the deep learning system, it can analyze large amount of data and it can discover patterns from it like images, text, video and audio, and we can derive insight from those patterns. Next is accuracy. So deep learning, they have high recognition accuracy when compared to machine learning, and this high recognition accuracy is a major factor for applications such as automated car and medical devices. And the last advantage is it outperforms other machine learning methods. So it requires minimal human intervention and it analyzes the data beyond the capabilities of other machine learning methods. Now let's see what is optimization in deep learning. So optimizers is algorithm that will adjust the model parameter during training to minimize the loss function. So this loss function is the error. So until you reach a minimum error, your model parameters will be adjusted. So it enables the neural network to learn from data by iteratively updating your weight and bias. So optimizer algorithms, it helps to improve your deep learning model's performance, and it will affect the accuracy as well as your speed training of your deep learning model. So next is, we'll see what are the hyperparameters in optimization. Hyperparameters are parameters whose values are set before starting the model training process, and these values is used to control the learning process, and these are the list of the hyperparameters. The first hyperparameter is number of epoch. So number of epoch is defined how many times your optimization algorithm iterates over your entire training data set. Next hyperparameter is sample. So it is a single row of a data set. Next is your batch size. So it determines the number of data points which is used in iteration of the optimization algorithm. Suppose you are having 100 images and you are going to divide it into 4 batches means, so your batch size will be 25. Next is your learning rate. It is a tuning parameter. It will determine the step size at each iteration while moving towards a minimum of a loss function. So next is cost function or a loss function. Cost function, it is used to calculate the cost, that is the difference between the predicted value which is generated by the model and the actual value which is generated by the training data set. Suppose your actual value is 50 and your predicted value is 54, means then your cost function will be 4. Difference between the predicted and the actual value. So last hyperparameter is weight. It is the strength of the connection between the two nodes it connects. So these are the optimization algorithms in deep learning. The first is gradient descent, next is stochastic gradient descent with momentum, mini batch gradient descent, Adagrad optimizer, RMSProp optimizer, AdaDelta optimizer and Adam optimizer. Now let's see briefly about each optimizers. So the first one is gradient descent optimizer. This is a simple optimizer. It is an optimization algorithm for finding a local minima of a differential function. So how it works? First it will start with an initial coefficients. We will take a random initial value and we will evaluate the cost. That cost is the error, and we will seek a lower cost, and the process it moved towards reducing the cost by adjusting the coefficients. So this iterative process, it continues till the local minimum is reached. So the local minimum is nothing but the value of a loss function that is minimum at a point at a local region. So your error has to be minimum, and this process iterates until we reach the minimum error. So next is your stochastic gradient descent optimizer. It is a variant of gradient descent optimizer, and stochastic means some random variable. So here we are going to take some random training data set from the whole data set. So instead of using the entire data set for each iteration, only a single random training example is selected to calculate the gradient and update the model parameters. So gradient is how much your weight is changing with respect to your loss function. So this is the algorithm for it. Step 1, initialization. First we are going to randomly initialize the parameters of the model. Next is we are going to determine the number of iterations as well as the learning rate for updating your parameters. So we have a loop here, stochastic gradient descent loop. We are going to repeat this step until the model converges or it reaches the maximum number of iterations. First step, we are going to shuffle the training data set. Randomly we are going to shuffle and iterate over each training example in the shuffled order. Then we are going to compute the gradient of the cost function of the current training example or a current batch. Then we are going to update the model parameters. How we are going to update? By taking a step in the direction of a negative gradient which is scaled by the learning rate. Then after updating the model parameters, we are going to evaluate the convergence criteria. Convergence criteria is the difference in the cost functions between iterations of your gradient. So your last step, it will return an optimized parameters. When it will return? Once your convergence criteria is met or the maximum number of iteration is reached, it will return the optimized model parameter. So in stochastic gradient descent, since only a sample from the data set is taken to reach the local minima, so the path taken by the algorithm to reach the local minima is usually noisier than the typical gradient descent algorithm. So here the algorithm path is noisier as well as it requires a higher number of iterations to reach the local minima. When your number of iterations is higher, what will happen? It will take a longer computational time which is more time consuming than your typical gradient descent algorithm. So next is your stochastic gradient descent with momentum. So stochastic gradient descent with momentum is an optimization algorithm which was traditionally built on the stochastic gradient descent by incorporating a momentum term. Here we are going to add an additional momentum term which is nothing but the moving average of your past gradient. This helps in optimization process to maintain the direction. So what happens when we are introducing this momentum term? Your noise, the algorithm path to reach the local minima will be less noisier than your stochastic gradient descent. So this is the algorithm for it. For step 1, we are going to initialize the parameters. First, we are going to select the initial parameter, weight and the bias. Then we are going to choose a learning rate as well as a momentum turn. Then we are going to initialize the velocity of each parameter to 0. So velocity is the change of gradient to the global minima. So already I said local minima is the value of a loss function is minimum at a point in a local region. Your global minima is the value will be minimum across the entire domain of your loss function. So the step 2, for each iteration, first we are going to shuffle the training data set, and after shuffling, for each individual training example, we are going to calculate the gradient of the cost function, and after calculating the gradient, update the velocity of each parameter using the momentum term. So your formula is V is equals to beta into V plus 1 minus beta into your gradient. So beta is your momentum term. Then after that we are going to update the parameters using the velocity. So parameters is equals to parameters minus learning rate into V, velocity. The third step, you are going to tune your hyperparameters. So you are going to fine tune the hyperparameters such as the learning rate and momentum turn based on the performance of the model. So final step, convergence check. You are going to monitor the convergence by tracking the value of a cost function on the training data set, and we are going to stop the process when the desired convergence criteria is met, and finally it will return you an optimized parameter values. This is the difference between SGD without momentum and SGD with momentum, and this is the local minima, and you can see the path here, the algorithm, it reaches the local minima. It is very noisier, but here it is less noisier. Next is mini batch gradient descent optimizer. Here it is a variation of gradient descent optimization algorithm, and it processes only a subset of a data in each iteration. Suppose you are having 100 images and you are going to take only a batch of it, for example 50 or 25. So mini batch gradient descent algorithm, it works as follows. Initialization, you are going to select the initial parameters, weight and bias, and set the learning rate and other hyperparameters. Then after that you are going to shuffle the training data to randomize the order of samples. Third step, for each iteration you are going to split the shuffle data into batches of specified size. I already said when 100 data are there, you are going to divide it into batches like 25, 25, 25, 25. Now for each mini batch, you are going to compute the gradient of the cost function using the current mini batch. Next is we are going to update the parameters using the computed gradient, that is parameters is equals to parameters minus learning rate into gradient, and the update is performed for each parameter. And this process is repeated until the model reaches the convergence or a specified number of iterations. So far we saw gradient descent, stochastic gradient descent and stochastic gradient descent with momentum and mini batch. So in all those algorithms, your learning rate will be constant. We have to first initialize your learning rate, and it will be constant throughout the training process. And next is Adagrad optimizer, adaptive gradient descent optimizer. So here what happens, it will adapt the learning rate for each parameter based on your historical gradient. That is, it will use different learning rate for each iterations. So what is the advantage here? We can eliminate the need of manual adjustment of your learning rate. So Adagrad optimizer algorithms works like this. For step 1, initialization, you are going to set the initial parameters, weight and bias, and choose the initial learning rate. Then afterwards you are going to initialize the historical gradient accumulator G for each parameter to 0. The second step, for each iteration you are going to shuffle the training data set, and for each individual training example you are going to compute the gradient of the cost function, and next is you are going to accumulate the square of each element of the gradient into a historical gradient accumulator. So your formula is G is equals to G plus gradient square. Then after that you are going to update the parameters using the adaptive learning rate. So parameters is equals to parameters minus learning rate divided by square root of G plus epsilon and gradient. So here we are going to add gradient, which is a small constant, to avoid the division by 0, because any number divided by 0 will become infinity. So to avoid that we are going to add a small constant epsilon. The next step, hyperparameter tuning, and here we are going to fine tune the hyperparameters such as learning rate and constant based on the performance on the model. And the final step, convergence check. We are going to monitor the convergence, and the training process is stopped when the desired convergence criteria are met. So, the disadvantage of Adagrad optimizer is, as your learning rate adapts automatically, what happens? It monotonically decreases your learning rate. So, when your learning rate decreases, what will happen? Your deep learning system, it cannot acquire new knowledge from the input data. So, to overcome this, we are going to use RMSProp, that is root mean square propagation. So, it is an advancement of Adagrad optimizer. Here the algorithm, it will keep the moving average of your square gradient of every weight, and it will divide the gradient by the square root of the mean square. So, this algorithm works like this. Step 1, initialization. Set your initial parameters, weight and bias, and choose your initial learning rate, and set a decay factor which is typical to 0. So, this decay factor is, first you will have a large learning rate. So, as your iteration goes, your learning rate decays or reduces drastically, and here we are going to assign it as 1 so that it will not go below the value of 1. So, the next step is, for each iteration we are going to shuffle the training data set, and for each individual training example we are going to compute the gradient of the cost function and update the accumulated square gradient for each parameter. So, your formula is E of g square is equals to rho into E of g square plus 1 minus rho gradient square. And then we are going to update the parameters using your adaptive learning rate. So, parameters is equals to parameters minus learning rate divided by square root of E of g square plus epsilon into gradient. The next step, we are going to fine tune your hyperparameters such as learning rate and your decay factor here. And final step, convergence check. We are going to monitor the convergence, and your training process stops when the desired convergence criteria are met. Your next optimizer is AdaDelta optimizer. So, AdaDelta is an optimization algorithm which is designed to address the limitations of Adagrad as well as RMSProp optimizer. So, the disadvantage of RMSProp optimizer is, initially we have to assign a value for a learning rate. So, Adagrad disadvantage is, it will adapt your learning rate for each iteration, and as it adapts the learning rate decreases monotonically. So, these two disadvantages we are going to overcome by AdaDelta. So, AdaDelta, it adapts the learning rate by using the running average of the square gradient. So, AdaDelta algorithm is this. First, initialization. So, select your initial parameter, weight and bias, and choose your decay factor which is typically close to 1. The next step, we are going to initialize two running averages here. First one is the running average of the square parameter update, and second is the running average of the square gradient. The third step, for each iteration we are going to shuffle the training data set, and for each individual training example compute the gradient of the cost function, and going to update the running average of the square gradient. Then finally we will compute the RMS of the parameter update using the running average of the squared parameter, and this is the formula, and we are going to update the running average of the squared parameters, that is E of delta theta square is equals to rho E of delta theta square plus 1 minus rho delta theta square. Next we are going to update the parameters. So, parameters is equals to parameters plus delta theta. Then finally we are going to check the convergence, monitor the convergence by tracking the value of the cost function, and we have to stop the training process when the desired convergence criteria are met. So, your final optimizer is ADAM optimizer. It is an adaptive moment estimation optimization algorithm, and it is a combination of RMSProp and stochastic gradient descent with momentum. Here we are going to use the squared gradient to scale the learning rate like RMSProp, and we are going to take the advantage of momentum by using the moving average of the gradient. So, ADAM optimization algorithm For step 1, initialization. First you are going to initialize the parameters weight and bias and choose the initial value for the exponential decay rates. Here we have two decay rates, beta 1 and beta 2. This is for the first moment and this is for the second moment. The next step, we are going to initialize two moving averages. First one, the first moment estimate, and second, M is the first moment estimate and V is the second moment estimate. So, a third step, for each iteration, we are going to shuffle the training data, and for each individual training example, first we are going to compute the gradient of the cost function, and second, we are going to update the first moment estimate, that is M, where M is equals to beta 1 M plus 1 minus beta 1 into gradient. And second, we are going to update the second moment estimate, that is V. V is equals to beta 2 V plus 1 minus beta 2 gradient square. Next, we are going to do bias correction for M and V. Why we are going for this bias correction? For faster convergence and stability of the training process. So, M cap is equals to M divided by 1 minus beta 1 T, and V cap is equals to V divided by 1 minus beta 2 T, where T is the iteration number. And finally, we are going to update the parameters. So, parameters is equals to parameters minus learning rate divided by square root of V cap plus epsilon plus M cap. So, step 4 is hyperparameter tuning. We are going to fine tune the hyperparameters such as learning rate and decay factor 1 and decay factor 2 based on the performance of the validation set. And final step, we are going to check the convergence, that is monitor the convergence by tracking the value of the cost function of the training set, and we are going to stop the training process when the desired convergence criteria are met. Thank you.